Then I'll start. So first, the warning, I'm going to rush through my slides. I think it's most useful for if you look at the code to see what the why the things are, to have it as a reference to see how things are as they are. And for that, I cannot really cut a lot of details. So you will be able to see, get the slides afterwards, but be prepared that I'm going fast through them. So first thing, what are loop transformations? So these have been introduced first in OpenMP 5.1, which are a new set of directives, namely the unroll and tile directive, which allows you to treat a loop in a different way as you have written in the code. For this example is you apply a full unrolling a loop, and it's handled as if you have unrolled the loop manually. Cannot only fully unroll the loop, but also do a partial unrolling, which typically looks like the example on the right. That's how compilers would optimize it. But for the sense of OpenMP, it makes more sense to handle the loop as like this, and it's a compiler stack afterwards to maybe try to remove the additional if conditions there for performance optimizations. You also are allowed to leave away the unroll factor, in which case it's a compiler's responsibility to choose an unroll factor, but you don't know it at compile time what it might be. You can also leave away the unroll or full class entirely. In this, which case it's completely up to the compiler what to do. It might do full unrolling, it might do partial unrolling. There might not be a loop after that. After all, the other transformation is tiling, which does as it says. It's tiles the loop nest. Concretely, it doubles the number of loops. Such you have tile loops. You have to take care that the inner tiles may not have all the iterations, so there might be complete tiles and partial tiles. One special thing is that you can compose these loop transformations. You can apply loop transformation and apply another loop associated directive afterwards. You can think of that your loop associative directive applies on what's coming after it. So in the case one, it applies on the literal for loop in the source code, nothing special here. But if you put a tile directive in between, the task loop applies to the output of the tile after you have applied, replaced the tile by the loops that it stands for. Next thing is we go a short overview into the Clang's compiler internals. Namely, the most important thing about its abstract syntax tree. Here, if you have an example on the left, and you get the abstract syntax tree dump using the command you see at the top. Each syntax element has its representation in the AST. So the OMP parallel 4 is represented by an OMP parallel 4 directive node, together with its schedule clause. The for loop that is nested inside of it has its representation, including its init statements, its loop conditional, its increment statement, and of course this loop body. What's a bit more complicated is that the entire thing is wrapped inside a captured statement. This is because the parallel 4 may need to be outlined in another function. And for this outlining to happen, it needs to know which variables are used inside to be outlined region. So this is done by this captured region, which shares the same implementation as for Lambda, most of it, but also adds this global thread ID thing, for instance, that are filled by the OpenMP runtime to inform the code what thread it is running on. You can think it as a syntactic trigger like this, as if you had a literal lambda in there. The class hierarchy looks like this. We had the OMP parallel 4 directive node, which is derived from OMP loop directive, which is derived from OMP executable directive, and everything is basically derived from statement. Note that the OMP parallel directive has a different hierarchy than the OMP parallel for directive, since the OMP parallel directive is not a loop associated directive, and only those are derived from OMP loop directive. The OMP clause hierarchy is unrelated to the statement hierarchy. So there's no common ancestor for all the nodes that appear in the AST, which might be confusing because if you get the children iteration, you do not get the clauses or the declarations, just the statements, and you have different iterators for iterating over clauses and declarations. This is why the implementation makes a lot of use of a visitor pattern, which is used for instance, these AST nodes are still needed to be dumped by the dump command or serialized, deserialized for C++20 module support. This is a rough architecture of Clang itself. The layer it's split into. We basically didn't need to change anything from the preprocessor upwards. The parser part is quite straightforward, not a lot to talk there. We have the semantic analyzer where most of the interesting thing happens, including this AST to AST tree transform, which is primarily used to instantiate templates. So you get a template, you instantiate and get another AST out of it, and we are going to use it to implement the loop transformation. So where you get a loop as input, you apply a AST transformation and get an unrolled loop out of it. After that, everything is passed to the code generation layer, which generates LLVMIR out of it. If you want to need more of that, I can recommend 2 talks of it. One tutorial and another talk of mine, where you also can see the same diagram. Please use the links there. So let's go into the first implementation there. The most forward thing is that we introduce new classes. So for the unroll and tile directive, called the OMP unroll directive and the OMP tile directive. But instead of deriving it from the OMP loop directive, we introduce a new class between the OMP executable directive and OMP loop directive for reasons that I'm going to explain later. We also extend the OMP class hierarchy for each of the clauses we need to support. It's also very straightforward. In practice, this looks like this. So we have an unroll directive for illustrative purposes applied to a partially unrolled loop. So as outermost loop, you have the fully unrolled loop, with the full clause. You have the one in the middle, which generates a partially unrolled loop to be fully unrolled by the other OMP unroll directive, and you have the body code of it itself. I mentioned that we would do the AST transformations, but those did not appear here. For explaining what we are doing, let's a bit explain what's another construct that Clang is using, the C++11 range-based for loop, which is defined by the C++ standard as syntactic sugar for what you see on the bottom left here. And this is partially also implemented as so-called implicit AST nodes, that is AST nodes that do not for things that do not directly appear in the source code, such that implicit cards. So we have these normal ones, in this case the body code, which appear on all the representations, but also AST nodes that only represent statements in the unsugared variant. And you see in the bottom, you have a list of nodes in the Clang source code of implicit AST and explicit AST nodes. So the OMP loop directive is another beast here. It does not have, it does have 37 implicit AST nodes. Some of them are per associated loops, so it can be more. And maybe fortunately, these do not appear if you get the AST dump. So they are hidden from the user. They still need to be serialized and deserialized for C++11 support, but it may not be obvious that they exist and they do not appear in the dump. So this is why we introduced the OMP loop-based directive, which itself does not have any AST nodes. But instead, we introduced these shadow AST nodes for the OMP unroll directive and tile directive directly, which is namely the AST node for the transformed statement, so after unrolling or after tiling. And we have another one for the pre-inits, which are usually used to compute the loop bounds, anything that has to be done before the loop itself. Practice, the AST dump of the transformed statement that you usually do not see looks like this. So again, you have an unrolled loop. Here you have the upper bound explicitly computed inside the for statement. But instead of applying the unrolling itself, our AST, we leave it up to the loop unroll pass, so the LLVM optimization pass, by using the same thing that the pragma Clang loop unroll count pragma uses. And as normal, we have the thing that is going to be unrolled. For the code generation part, it's basically just past the AST node that has been computed in SEMA. If it's standalone, nothing has to be done because it's already applied on the AST. So no code transformation needs to be done in the code gen layer. If it's been used, if the unrolled or tiled loop is being consumed by another loop associated directive, then the logic for the OMP loop directive will have analyzed the transformed loop, and everything that has been analyzed will become part of the numerous implicit AST nodes of the OMP loop directive. So we have a second implementation that uses the OpenMPIRBuilder. First, what's the OpenMPIRBuilder? It's another component we basically put in between the code generation and the IR builder that does higher level things for emitting OpenMP codes. For instance, you can tell it, hey, please emit an OpenMP barrier, which is usually a call to the OpenMP runtime. The main advantage is that you can use it from other components than Clang. For instance, it can be used by Flang to implement OpenMP for Fortran. Flang itself lowers to MLIR with the OpenMP dialect. That dialect can also be generated by TensorFlow, so get more independence on what source language you're using. We are basically reusing the same statement class hierarchy, but we add a new one for representing an OpenMP canonical loop. This takes inspiration again from the desugaring of the C++ for loop, but instead of making it desugar for iterating over C++ iterators, we desugar it by first computing the distance and then using that one to iterate over a normalized loop. Normalized here means it starts with 0 and has a step size of 1. And having that one, we from this normalized loop iterator, we compute back the value that would be expected by the loop body code. This is basically the requirement of our OpenMP canonical loop, that you know the trip count in advance before you start executing the loop, so you know how many threads you need to spawn, for instance. So the OpenMP canonical loop has as its child node the loop statement itself, so it does not replace the for statement or CXS4 range statement. But it also has additional information about how to compute the trip count of that loop in advance, which is the distance function, which is basically lambda, also captured statement, as we have seen before. And also another lambda, which takes a normalized logical iteration number and computes the user loop variable from it. In practice, the AST of that looks like this. We have an unroll. We have the loop itself with the for statement that hasn't changed itself. But in addition to that, we have the OpenMP for loop, which has this to capture statement and additionally a reference to the user loop variable. We augment the OpenMPIRBuilder for functions, first with a class for representing such loops, which have to be side effect free and represent a logical iteration, have a logical iteration counter or induction variable. We have in the OpenMPIRBuilder itself functions to create such loops as a CanonicalLoopInfo, which we can pass to functions or methods that take this CanonicalLoopInfo as an argument and either transform it or maybe not return another canonical loop, but implement a workshare loop, for instance. The structure created by this like this. So, for instance, we have a pre-header, where usually the things to compute the loop bounds, like the pre-inits we mentioned before, goes into, and the loop body somewhere in the middle, where the user code for the loop body goes into. The implementation of that one is then quite straightforward. Whenever you, in the code generation layer, if you encounter an OP canonical loop, you ask the OpenMPIRBuilder to create this CanonicalLoopInfo and push it onto the stack. When you get a loop associated directive, you first emit all the OMP canonical loops in the associated statements, and then look for the loop stack for these OMP canonical loops that you can pass on to the methods that implement these directives. The only difference for a loop transformation is that they return another canonical loop info that you also push back on the stack. The status of that one is that's basically implemented, as I mentioned. The only thing is the unroll loop, which I just put up on review this morning. So that has not been committed yet. For the future, I hope to implement more such things like loop interchange transformations, or also apply loop transformation not only on the outermost loop of this loop stack, but for any loop that is there on the stack. And that's it. And I hope you have interesting questions if there's time left.
Thank you, Michael. Yeah, we have a few minutes for questions. Any questions up? Okay. I want to ask something. How composable it is to use those transformations with other type of transformations that are available through this Pragma interface?
With the other one, if you've seen this Pragma Clang loop, for instance, it's not composable at all. This is one of the deficiencies that I, for instance, talked about in the LLVM developers meeting 2019. The result of it is basically unpredictable, but typically if you try to combine them, the Pragma Clang loop is just drop. In the sense of OpenMP 5.1 and the standard, only those defined in the standard as composable by each other, which is the unroll directive and the tile directive, which produce canonical loops or generated loops that can be used for other loop associated directive. But there's no guarantee at all that these can be combined with a Pragma unroll, for instance, that Clang also support.
I see. Okay. Any other questions?
Yes. So what do you think is the possibility of sharing some of this effort with a higher, like MLIR OpenMP dialect, for example? I mean, there's transformation being done at that level as well, right?
Yes. So I expect that there will be in the OpenMP dialect, we add tile and unroll constructs or operations itself, which directly map to calls to the OpenMPIRBuilder methods as we've done before. there would be opportunity to also directly apply these transformations on MLIR itself, which would allow doing optimizations on the result of that on the MLIR level itself, if that's something we wish we need. But for now, I would just do the straightforward way. We have one OpenMP directive, which corresponds to one OpenMP direct operations in MLIR, which is lowered by the OpenMPIRBuilder.
Okay, thanks.
All right, thank you, Michael.